Hello everybody and welcome to the homework helper for section 3.4. The very first section here, it's asking us to recall the meaning of division. So all that we're doing is we're looking at what our f of x is, what our g of x is, and then setting it up like long division as we did the last section or the section before. So all that we're going to be doing here is taking our g of x, x plus 7, and dividing that into our f of x, x plus 7 times 2x minus 3. And remember, whenever we're doing long division, we're trying to see, what we're going to put above here, what goes here in this part, is whatever we have to multiply x plus 7 by to get what's underneath our long division sign here. So what do we have to multiply x plus 7 by so that we have x plus 7 times 2x minus 3? Well, that's just 2x minus 3. Because sure enough, if we were to multiply these together, we would get x plus 7 times 2x minus 3. When we subtract those, we're going to get 0. Thus, we have divided successfully. 1, 2, 3 are going to ask you to do that. 4 is going to ask you something a little bit more complicated because we're going to be dividing between 3 terms. We have an f of x, we have a g of x, and we have an h of x. So you're going to have to process your way through all of those and just do which ones are being asked of you. Look to see what we have to multiply it by to get it to be those results. Number 5 is going to be incredibly challenging. So puzzle with it as much as you can. I'm pretty sure G of the A is easy, but the B is going to be a little bit hard. So just kind of keep that in mind as we go forward. Okay. The set is polynomials, multiplying polynomials. This is just going to be whichever method you prefer. We've learned the box method. We know about foiling. Use whichever method makes the most sense to you. But ultimately, we're going to be doing this pretty much the same way as always, right? When I look at number 7 here, we have x times x squared. So that would be x cubed. X times 3x, which would be 3x squared. X times 9, which would be 9x. Negative 3 times x squared, which would be negative 3x squared. Negative 3 times 3x, which would be negative 9x. And then negative 3 times 9, which would be a negative 27. From here, all we have to do is combine our like terms. We have an x squared here, an x squared here, an x here, and an x here. And look at what we end up seeing. We see that these will cancel, this will cancel. So we're only left with x cubed minus 27. You're going to see that pattern a couple more times. I just want you to keep looking for that pattern. Keep looking to see what that pattern will be doing here. And we'll go from there. All right. Final section. No, not quite the final section. Next, the final section. We'll be working with Pascal's triangle. There's a very unfortunate typo right here. This 3 should be a 4, so let's fix that real fast. When we're looking at Pascal's triangle, keep in mind that the coefficients as we build in our complexity, as we take some a plus b, or x plus a in this case, and raise it to different powers, our complexity builds in a pattern where each number is the addition of the 2 numbers above it, right? 3 plus 3 is 6, 3 plus 1 is 4, etc. So we can continue to build this down for further generations, further powers on the triangle. So for example, x plus a to the 5th, we can just build this triangle, right? We'll start with a 1, we'll end with a 1, but 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. And so we have those coefficients. And so for number 12, for example, when we build this, these are our coefficients. So I know that I'm going to have an x to the 5th, because I always start with x to the highest power, x to the 5th plus 5. And then now my a powers will increase while my x powers decrease. So a to the 1st, x to the 4th, plus 10. A is going to increase to squared, x is going to decrease to cubed, plus 10. A is going to increase to cubed, x is going to decrease to squared, plus 5. A is going to increase to the 4th, x is going to decrease to the 1st power, plus 1, in this case, a to the 5th. And from here, all we have to do is plug in what our A is. Okay, we're just plugging in what our A is. So this is going to be x to the 5th plus 5. Our A is 1, so times 1, x to the 4th plus 10 times 1 squared x cubed plus 10 times 1 cubed x squared plus 5 times 1 to the 4th x plus 1 to the 5th. And what's super easy about this one is 1 to any power is just 1. So our final answer is just x to the 5th plus 5 times 1 is just 5. 5x to the 4th plus 10x cubed plus 10x squared plus 5x plus 1. Because all of these 1s to powers are just 1. Okay? And that's it. That's our answer. But we can do some other more complicated ones. Like I'll do number 16 right here. Okay? For this one, I don't have to build it. It's already given to me. We know what the 4th power is. It's given to us in this line here. So I know that I'm just going to build this, and I'm just going to plug in 2 for my A. So I'm going to start with x to the 4th plus 4ax cubed. In this case, my A is 2. So 4 times 2 x cubed plus 6a squared x squared. So 6 times 2 squared times x squared plus 4 times a cubed, 2 cubed x plus a to the 4th, or in this case, 2 to the 4th. And now I just need to simplify all of this. So this is going to be x to the 4th plus 4 times 2 is 8x cubed. 6 times 2 squared. 2 squared is 4. 6 times 4 is 24 x squared plus 2 cubed is 8. 4 times, this is 8. 4 times 8 is 32, so 32 x. And then 2 to the 4th is 16. So this becomes my final answer. All right. So you just need to do that for all of those there. For number 17, where we have a 3x, what you're going to do is everywhere there was an x, you're going to put a 3x. So when we're talking about this x squared, that would be a 3x squared, so the 3 would be squared on that. So that one's a bit challenging, so best of luck on that one. All right, let's go to the go topic. Examining transformations on different types of functions. So to be able to do any of these, we have to know what the basic form of these graphs look like. So this is linear, right? It's x to the 1st power. So I'm just going to graph it real fast. So I'm going to use a couple different colors to try to make this work. Okay. So the basic form of a linear equation is just y equals x. And what does that look like? Well, that's going to be a straight line with a slope of 1, right? So this is y equals x, just like this here. Okay? Up 1 over 1, up 1 over 1, etc., etc. Y equals x. So then if I were to do that plus 2, I would have to move up 2 on my y-axis, but otherwise the shape stays the same. Like so. So this plus 2 is telling me to move up 2 units. Let's do that for a quadratic here. Okay, this is a basic parabola. So if I'm going to draw just the most basic version of it, I'll do that in red. That would be y equals x squared. So I'm going to graph the parent graph first, right? So 0 squared is 0, 1 squared is 1, 2 squared is 4, so 2, 1, 2, 3, 4. 3 squared is 9, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then going the other way, it's going to mirror it, right? Because -1 times -1 would be 1, Negative 2 times negative 2 would be 4. Negative 3 times negative 3 would be 9. So on and so forth. So we get this parabolic shape. Okay. Now, when I actually do the transformation of the plus 2, all I do is I move this up 2, but the basic pattern remains the same. Over 1. When I go up 1, I go over 1. If I go 2, I go up 4. 1, 2, 3, 4. And you see that I'm doing this 2 and 4 based from the vertex of the parabola. The vertex of the parabola. That'll be up 2 from here. And so on and so forth. 2, 2, 2. And so my parabola is just 2 units above my other. Again, that just means I go up 2. All right, let's do the same thing with this exponential. So the basic form of an exponential with a base of 2 would be y equals 2 to the x. Okay, let's go ahead and plot this parent graph. So when x is 0, 2 to the 0 power would be 1. So 1. First power would be 2. 2. Second power would be 4. 1, 2, 3, 4. Third power would be 8. 1, 2, 3, 4, 5, 6, 7, 8. Fourth power would be 16. We're doubling each time. 9, 10, 11, 12, 13, 14, 15, 16. So it just goes off the graph, right? Because we're doubling at each step. 1, 2, 4, 8, 16. That means going backwards, we're going to be halving by each step, right? To the negative first power would be a half. To the negative second power would be a quarter, a 16th, a 32nd, a 64th, a 128th, etc. So we have our graph that looks like this. And so when we do our f of x here, where we're adding 2, again, all that we're doing is we're moving up 2. So now instead of crossing at 1, we're going to cross at 3. But otherwise, the pattern is going to stay the same. Up 1, over 1. Up 2, up 4. 1, 2, 3, 4. Etc., etc. Up 2. Yeah. And then this will approach down here. So we end up with that as our shape. All right, let's go on and look at some of these other ones. Okay. So now what we're going to be doing is we're going to be doing a stretch, and we're going to be changing where our starting point is. Okay. Because our general form, and we're seeing it kind of over and over and over again, is we have a y equals a x minus h plus k. Whoops, that's not on the screen. There we go. Where hk is our starting point. Okay, this is normally the origin in most of our lines, but when we're talking about the parabola, that's our vertex. So that kind of tells us how we're shifting vertically or horizontally. And the A is our stretch. So given the basic patterns that we saw, when we're looking at our A, we're going to be manipulating it based on that. So what we see here for 21, 22, and 23 is we're shifting, okay, we're shifting over 2, okay, so we're going to move back 2, but then we're going to stretch by 3. So look at here. Here's a linear equation. It's to the first power. Normally, like we just did, we saw that we would start at 0, 0. But I see that I'm shifting back 2, right? My hk here, my hk would be 2, 0, right? Minus 2, minus hk. So instead of starting at 0, 0 like I did in the parent graph, I'm going to be starting instead at 2, 0. So 1, 2, 0. Okay? And before, I remember I would go over 1, up 1, over 1, up 1, right? That was our parent graph. We would go over 1, up 1, over 1, up 1. Well, now I'm doing triple that. I'm doing triple that because that's my A. My A is my stretch. So I'm going to go over 1, up 1 times 3, which is 3. Before I'd go over to up 2. Now I'm going to go over to up 2 times 3, up 6. 1, 2, 3, 4, 5, 6. Okay, and then likewise in reverse. Okay, so we're gonna go backwards the exact same way. 1, 2, 3, and so this will create our new line based on those transformations, based on our A stretch. Okay, and based on a new starting point. Okay, likewise with number 22. With number 22, we're going to do the same thing. This time we are given a quadratic, so we know this is going to be parabolic. So we're going to do the same thing, quadratic. We're going to do our HK. Okay, our HK is also 2, 0. So 1, 2, 0. 1, 2. Okay. And whereas our parabola before, we'd go over 1, up 1, over 2, up 2 squared, so that'd be 4. Now we're going to stretch it by 3. So over 1, up 1 becomes over 1, up 3. And then likewise in reverse, because it's parabolic. Over 2, up 2 squared becomes over 2, up 2 squared times 3. So 2 squared is 4 times 3 is 12. So I'm going up 12 units. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm already at the edge of my graph. Okay? Because I'm stretching it by 3 each time. Okay? Based on the basic pattern that we did before. Okay? I'm going to let you to your devices to do the rest of these, but take your time with it. Know the parent graphs, see how those behave. And from those initial graphs, you can then see how each of these things are manipulating it. But this is your roadmap on how to do things. Okay? The HK tells us our new starting point, and the A shift tells us how much we're stretching it compared to the parent graph. All right, good luck everybody.